This is integrated circuits. So one thing that I do want to address is that the class is taught jointly between the undergrads and the grad students, where the grad students get an extra couple of problems here and there. For administration purposes, I have just put all of the grad students in the undergrad section on Moodle. So Stephen, you should see right now that you're enrolled in 438 and 557-003 on Moodle. I'm not going to put anything on the 557 thing because I don't want to waste my time uploading stuff twice. I'm just going to put everybody in the undergrad version and administrate the class from there. Howdy, Leslie. All right, so let's talk about the syllabus. As you can see, because you all are literate, this is the syllabus from last year because I haven't finished the one for this year. So we're going to talk about things here. Okay. So obviously my office hours and all that kind of stuff are going to be different. I'll get those to you in a little bit. All of this boilerplate stuff is normal, boring things. Then we have stuff about homework, design projects, and exams, and then the grade distribution. So this is really what I want to talk to you guys about. So there are a lot of different components of this class. There are theoretical bits of which I'm going to ask you questions about. We're going to be using electric in order to do schematics and layouts for circuits and things like that. We're also going to be doing like, pen and paper, circuit design and all that kind of good stuff. And all of those things are really inextricably linked. So me having everything delineated out like this usually actually doesn't particularly work very well. So what I am thinking about doing is literally just saying the only grade in this class is going to be exams. They are all going to be take-home exams, and they'll all have a theoretical portion, a design portion, and an analysis portion. And my hope is for there to be like 4 or 5 of these exams, and effectively you just treat it like a homework assignment. I'll give it to you, like I'll put the first one up this week. It'll be due in 2.5 weeks or something like that after we finish covering the material kind of thing. I'm calling it an exam simply because I'm supposed to give exams, but it's really just a glorified homework assignment. Does that sound unreasonable? And then all of them will be graded equally, and however many of them we get through is how much they're worth, kind of thing. Don't know what's going on there. All right. So I think that's how things are going to go. All right, so now let's talk about what we're going to be doing in this class. The first several weeks are going to be spent talking about the CMOS fabrication process, but we're not going to talk actually about the fabrication process itself because that's what your ELEN 437 class is at least partly about. Instead, what we're going to do is we're going to start with the inverter that I asked you guys to make in electric way back in 335. It's okay if you don't have that, but we are going to be using electric in this class a lot, so you need to have it, up and running probably by the time classes start next Monday. And I'll upload all the download information and setup information to Moodle here after class. But we're going to start with the inverter. This class is going to be about analog integrated circuits, but the inverter is a good, simple example of an integrated circuit in as much as it utilizes both NMOS and PMOS technology in the same circuit. And then we're going to literally flip it so that instead of looking at it from a top-down perspective, which is how we designed it back in 335, we are going to be looking at it from the ground up, talk about substrates and local substrates, and then literally move our way through the layers that are used in the fabrication of that particular integrated circuit to talk about how those layers are used in analog integrated circuits. Once we get through talking about all of the different layers and things like that and their utilization in analog integrated circuits specific to the on-semiconductor C5 process, then we are going to get into a very brief review of what was covered in electrical engineering 335 and 336, just rehashing what the fundamental building block of analog integrated circuits are. And that'll be like the first half of the class. And then the second half of the class is we are going to design an operational amplifier from the ground up. Integrated circuit design, particularly op-amp design, is actually the hardest part of anything you would ever learn in a class like this. The reason why it's taught as opposed to digital integrated circuit design is because if you can do the analog integrated circuit design and you understand what goes into an op-amp, like current mirrors, differential pairs, frequency compensation components, input and output stages and all that kind of stuff. If you can do that and it makes sense, all other analog components are trivial in comparison to the op-amp. All digital integrated circuits are even easier than the most trivial analog. So every integrated circuits class is effectively set up to teach the op-amp because it's the hardest thing you can design. And then everything past that is really just using those building blocks from an op-amp in different ways. Okay. So with that explanation of what it is that we are going to be doing out of the way, I now will bring your attention to our inverter circuit. So this is an inverter. It doesn't meet all the very specific design criteria that I gave you guys in 335. It's slightly more simplified in as much as the constraints on the size of the transistors were largely ignored. But if we were to simulate this, which I have already done, we would find that it obeys what an inverter is supposed to be doing exactly. If our input voltage, which is listed in green, is high, our output is low. When our input voltage is low, our output is high. We are inverting that simple binary signal, okay? So in this circuit, starting from the highest potential, which is at the top, down to the lowest potential, we have a voltage supply rail. We have our body connection for our PMOS circuit, or excuse me, our PMOS transistor. Here we have our PMOS transistor, a metal run. Here we have our NMOS transistor, the body connection for our NMOS transistor, and then another supply rail. So this circuit is perfectly symmetrical the way that I have laid it out. So what I'm about to do is effectively draw what you would see if you put a dashed line from this point in the circuit to this point in the circuit, and we're able to cut this circuit literally in half, turn it 90 degrees and look inside, okay? So now we get to the colored pens portion of the class. So I'm going to start by labeling this as the side view of a CMOS inverter. On the bottom, we are going to have our substrate. And I cannot draw this line straight to save my life, which means at some point I have to get off my lazy butt and make these into slides. But today is not that day. So this portion right here is our substrate. And I'm going to try to make a little legend here to differentiate what the different layers are. Okay. So, in order to do our NMOS transistor, what we are going to have is a region that looks something like this. And this is our N active region. It may also be called the N diffusion region, and typically includes a select layer as well. And we'll talk about what that statement means when we address how we use this particular N and P active regions in a couple of lectures, okay? We also have a P active region here, which serves as our body connection. For our PMOS transistor, it's going to be composed of effectively the exact same thing as our NMOS transistor, except the N and P active regions are going to be flipped. Okay. So we're going to have something like this. Literally the exact same layers are being used, but to get the opposite effect due to the opposite doping concentrations. And then we are going to have this special guy right here that entirely encapsulates that NMOS transistor, excuse me, PMOS transistor. And this is the N-well layer. And we're going to be talking about it today once I finish drawing this picture. All right, so we're going to move up from the surface of the substrate now. And all of these bits are going to be in different kind of shades of gray, so I'm going to figure out how to do that here. So we're going to have this bit right here, and I'm going to put speckly little dots in there that are randomly oriented. And this is what's known as our field oxide layer. There will be another portion of field oxide here. And here. And all the way out to here. Over here like so. Here like so. And then out to the edge. Then we are going to have guys like so, which are serving as our contact layer. Before we move on to the next highest layer, we have, all right, I want that to be in pink. This guy right here, which is our polysilicon layer. Now for the inverter, we only need a single polysilicon layer. But in the creation of some analog integrated circuits, multiple polysilicon layers are used to do several different things, like form capacitors, form resistors, and things like that. And so when we start talking about the polysilicon layer, I'll introduce those other concepts as well. Now, we're going to add on to our field oxide layer by effectively encapsulating polysilicon like so. And then we're going to have effectively our final layer for this particular configuration. This guy right here, which is going to be our metal 1 layer. And in most analog integrated circuits processes, we usually have access to more than one metal layer. So we use those to make connections between different parts of our circuit. We can also form capacitors with them. We can use them for very low value resistances if we get creative about things, lots of different regions. The metal layers are also how we get signals on and off of our chips as well. And we'll talk about all of that kind of stuff. Okay. Yes, yes, it is. All right, so this is what the basic structure of our inverter would look like. Like I said, if we drew a vertical line from top to bottom right through the middle of that chain of elements, slice this guy open and looked in from the side, okay? So instead of this top-down view, we are large that is used to actually design integrated circuits on computer applications. We are going to use both that top-down view and the side view like this, because I find that the side view is actually a little bit more informative, as we can see more easily where parasitic and capacitors and things like that are actually going to come from. Okay. All right, so how are we feeling thus far? We at least have an idea of what it is that we're going to be talking about. Okay, so if we wanted to fabricate this inverter, the first steps that we would take would be effectively preparing the substrate in order to have this P active region deposited, this N active region deposited, this N active region deposited. We would need to have this N well deposited, this P active region, this P active region, and this N active region. So we're going to start effectively with the substrate and then work our way up. All right. So substrates. Hopefully fairly obvious, but CMOS integrated circuits are fabricated on silicon wafers. Typically, an integrated circuit itself, when we purchase it, is on a die, okay? So it is some rectangular form of silicon where, let's call this a CMOS die. And this is our top view. And then this is our local coordinate system. So here is the Y direction. Here is the X direction. And then the Z direction is oriented orthogonal out of the surface of the die. And then we have our cross-sectional view or side view. That is simply the top surface of the wafer up here and the bottom surface of the wafer down here. And like I said a few moments ago, we're going to wind up using both of these views to figure out how things work together. And our local coordinate system for this view is that up is in the Z direction, out is in the X direction, and out of the page is in the Y direction. So these silicon wafers can be doped either using a diffusion process or an ion implantation process with donor atoms like phosphorus or arsenic to make N-type wafers, or acceptor atoms like boron and gallium to make P-type wafers. We learned all of this crap way back in 335, okay? Typical doping concentrations for raw silicon wafers range from 10 to the 13 dopants per centimeter cubed, which we consider lightly doped, to 10 to the 16 dopants per centimeter cubed, which would be a medium doped wafer. We never really have highly doped wafers because we don't want to start at the upper end of the spectrum and then have to figure out how to put things on top effectively, okay? So the most commonly used wafer for CMOS circuits is a lightly doped P-type wafer where we're using the 100 crystal plane as our surface, okay? So what kind of crystal structure does a silicon wafer have? Or silicon have, for that matter? You guys remember? Should have learned this in 334. A diamond crystal structure. Absolutely right. Diamond crystal structure is one in which we have a face-centered cubic crystal structure interposed with a second face-centered cubic crystal structure that is a lattice distance of A/4 away from each other. I can't draw that for shit. So instead, I'm just going to draw a simple face-centered cubic structure real quick here. So let's draw a cube. Like so. It's already looking not particularly cube-like, but it'll be okay. Didn't do that right. There we go. Typically speaking, we would have atoms on all of these corner points in the center of each face. And then there's also a second atom that's effectively A/4 by A/4 away from every one of these points as well. That's not particularly important. That's just getting into the structure. What I want to talk about is the crystal planes really quick here. Okay. So the face that I've drawn or outlined in purple belongs to the 100 family. Okay. It has the lowest density of silicon atoms for a crystal plane in a crystalline piece of silicon. Okay. Then we have this plane, which is of the 110 family. Okay. And then finally, we have this plane, which is of the 111 family. And it has the most silicon atom area density. Okay. These different surfaces have different electrical and mechanical properties, and so are used for different types of things, depending on what we're looking for. Okay. So for electronics, it's overwhelmingly the 100 plane, sometimes the 110 planes that get used. For microelectromechanical systems, it depends on what shape it is that we're trying to pattern in our silicon as to what plane we're going to use. You'll learn in your microfab class, if I'm making you take it, that each of these different crystalline planes constitutes different etch rates and all kinds of things that lead to the different structures that you can get and their utilization. The reason why the 100 plane is used in CMOS electronic fabrication is because it effectively yields vertical sidewalls when we etch or implant things into it, so that we don't have weird pyramidal shapes all throughout everything where we have structural gradients. We instead have nice rectangular wells when we start, and then when we heat the crystal up and things tend to diffuse, the corners get a little bit rounded, but it still plays nicely with everything that we're trying to do. Okay. So in these P-type wafers, so let me write this down here. P-type wafers are the most commonly used substrates in industry. Does anybody have any idea why that might be? It's kind of a dumb reason. Let's start with that. When I taught you guys 335 and 336, what type of transistor did we focus on mostly? So what I mean by that, when we were talking about BJTs, did we spend more time on NPNs or PNPs? NPNs. When we were talking about MOSFET transistors, did we spend more time talking about NMOS transistors or PMOS transistors? NMOS transistors. P-type wafers are the most commonly used substrate in industry because you can directly put in an N-type transistor into them without any extra work. And since that's what most people learn more about, that's the one that gets used the most often, even though the opposite type of device literally behaves in the exact same way and all that kind of good stuff. Now, there are some electrical reasons why we typically tend to prefer N-type devices. We have a bit higher carrier mobility and things like that. Typically means we get to make things a little bit smaller, but it also literally goes to our familiarity with using the N-type device as the baseline for practically everything when we're learning this stuff. Okay. So NMOS transistors are fabricated directly in our substrate. What about P-type transistors? Since we're dealing with CMOS process in this class, I'm going to just say PMOS from here on out. So how do we do a PMOS transistor if we have a P-type substrate? Well, let's scroll up and look, because we've already seen it. We put it inside an N well, where the N well serves as a local substrate for that PMOS transistor. Okay. So how do you think N wells are created? We'll talk about their utilization because they are used for local substrates and a few other things here. How do you think this happens? Not a trick question. How did we make a PN junction? We talked about PN junction fabrication back in 335, right? You start with a chunk of crystal of one particular type, and then you have to dope it with the opposite type. If you dope it at the same doping levels, you get neutral crystal with a bunch of ionized donors that cancel each other out. In order to flip that region from P-type to N-type, we have to compensation dope it, meaning we have to put more dopants in that region, so more N-type dopants in that region than there were P-type to begin with, in order to flip it over to the opposite type of concentration. This is counter doping or compensation doping, so I'm going to write that down. Creation of the N well is accomplished by counter doping or compensation doping. Of the substrate. I'm going to put here ND, the number of donor atoms, has to be greater than NA, the number of acceptor atoms, where NA is effectively the background level of concentration of the wafer itself. So we need to put more donors in to that particular region in order to flip that material from P-type to N-type. Now, what is the result of this compensation doping? What I mean by that specifically is we have a P-type wafer that we start with, meaning that roughly 1 part per million of the silicon atoms in that chunk of silicon have been replaced by a different atom, either directly replacing at the lattice points or interstitial replacement, meaning that it gets shoved kind of between the bonds and all that kind of stuff. So it's making our crystal impure. Then we go in on top of that and put even more not silicon atoms in that space. So if we do compensation doping, are we replacing the acceptor atoms with donor atoms? No, we're replacing even more silicon atoms with something that isn't silicon, which tends to degrade the crystal as a whole, makes it not have exactly the electrical properties that we are expecting. Now, this is how we've been doing things forever, so it's pretty well defined and pretty well behaved. But what we see is that electron hole pair, that's what this abbreviation EHP stands for. We're going to talk about electron hole pairs a lot, so I'm not going to write it out ever. Recombination causes the acceptor atoms to ionize no free holes, which tends to increase scattering and lower carrier mobility. Effectively, all that means is we have a nice uniform periodic crystal structure and we are trying to pass electrons through it to have this thing carry a current. The more impurities we put in there, the more things electrons have to bounce off of and the slower they move. That's it, okay? So this result is often called excessive doping effects, and we can remediate this problem by using what's called a twin well process. So let me draw a twin well process here. So let's write this down. Excessive doping effects can be remediated using a twin well process. And I'm just going to do a quick and simplistic picture here just to kind of illustrate what's going on. So in a twin well process, we're going to have our N well over here, but we're also going to have a P well here into which we deposit our devices. Just quickly drawing things. So we have an NMOS transistor on the left-hand side and a PMOS transistor on the right-hand side. Our substrate, in this case, is lightly doped N4P. So effectively, if we start with a very lightly doped background level, we can achieve flipping the doping concentration to the opposite side without using as many impurities, which limit the amount of scattering effects and things like that that we see. So in a twin well process, it really doesn't matter what your type of wafer is, as long as the dopant concentration is as low as it can be while still having those favorable electrical characteristics. You actually would not use an undoped silicon wafer because it doesn't have the right electrical performance to actually make good electronics. Okay. All right, so how do you guys feel about substrates? We've talked about the different ones that we can use, how to make localized substrates, all that kind of good stuff. Anybody have any questions, comments, or concerns? All right, so I have, let's see, 10 more pages of notes about using NWell as other things. So let's take it easy for today and let me have time to go finish the damn syllabus for you guys. And we'll knock off here for now, and then we'll pick up continuing talking about utilization of NWell, the NWell layer on Monday. Does that sound groovy? All right. Thank you guys for your time, and I will be chastising, let's see, 1, 2, 3, 4, 5, 6, 7. 3 of you for not showing up. None of you, obviously, because you're here, for missing this class, which I thought I made pretty damn clear is a terrible idea to not show up for. So anyway. All right, have a good rest of your weekend. Hopefully your classes and all that kind of stuff are going well. I don't know how they couldn't be, they just started.